Excuse me. Alrighty. Well, we're going to get started. Hopefully everyone else gets here shortly, either in person or virtually. So today we will be doing our kind of practice activity with our chi-square test for goodness of fit. Looking at some different parts of how we do that using a Desmos activity. And hopefully that'll help make a little more sense of this new test. So I'm going to put the link for this activity in the chat. Sorry, one. And there we go. All right, so the link should be there, so you should be able to join directly into the activity. If for some reason the link is not working, you can always go to student.desmos.com and find our class period 3 and the AP Stats 11.1 activity. All right, well, we're going to get started. Hopefully you can join the activity soon if you have not done so already. As I've done in the past, some of the first few slides here will just be review of what we saw yesterday, so that we're all kind of like remembering what that stuff was and we can then use it. So that's what we're going to do first. So we can now go boom. All right, so our first thing here, just an intro here, our chi-square test for goodness of fit. That's what we started yesterday in section 11.1. The chi-square test for goodness of fit allows us to test a claim about a distribution of categorical data. This is different than the previous inference methods we have used because it allows for testing the evidence for or against an entire distribution of categorical data, rather than just one value within the distribution. So rather than testing each value in a categorical distribution against an alternative, which would be very time consuming, we can test the whole distribution with the chi-square test for goodness of fit, which can be much more effective. All right. This is how we calculate our chi-square test statistic right here. This is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-squared equals the sum of the each observed value minus its expected value squared divided by the expected value. All right, where the sum is over all possible values of the categorical data. And so this is how we calculate essentially our test statistic that we'll then use on table C based on degrees of freedom, which we'll define again in a moment. Right. We have our chi-square distributions. This is what our table C is based on. All right. And I know that writing came out really small, so I do apologize. Hopefully on your own Desmos, it's a little more clear to read. However, it does say the chi-square distributions are a family of density curves that take only non-negative values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square test for goodness of fit uses the chi-square distribution with degrees of freedom equal to the number of categories minus 1. All right, so however many categories we have for that categorical variable, minus 1 is our degrees of freedom. It does not depend on the sample size. All right, and then some things to keep in mind. As the degrees of freedom increase, the density curves become less skewed and larger values become more probable. All right, the mean for a particular chi-square distribution is equal to its degrees of freedom. All right, for degrees of freedom greater than 2, the mode or peak of the chi-square density curve is at degree of freedom minus 2. So these are some things to keep in mind. As with any inference method, we do have conditions to check. before performing that method. Right? Our conditions for performing a chi-square test for goodness of fit is the random and 10% condition that are the same as the random and 10% condition that we've seen for every other inference method we've done in this class. The large counts condition is slightly different. Large counts is saying that all of our expected counts, so the expected number or expected count of each category within our categorical variable all have to be at least 5. Previously, with our proportions, we needed to have the number of successes and number of failures being at least 10. Right? In this case, it's all expected counts are at least 5. We could have any number of categories. All of them must be at least 5. And then we can put it all together into our chi-square test for goodness of fit. Right? If the conditions are met, right, we can do our test to determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category. We perform a test of the null hypothesis, where the stated distribution of the categorical variable in the population of interest is correct, or the alternative that the stated distribution of the categorical variable in the population of interest is not correct. This is probably the easiest way to write those types of hypotheses, rather than trying to say that the proportion of blue is equal to this, and green is equal to something else, and red is something else, and listing each parameter value. We can just say, hey, the stated distribution of the distribution of the color of M&Ms is correct, right? Or that it's not correct. It's easier that way. We start by finding the expected count for each category, assuming that the null hypothesis is true. Right? That means we base this on the fact that what they've told us is the correct proportions, and we multiply that by the size of the sample, and we get an expected count. Right? When you then calculate the chi-square statistic, chi-squared equals the sum of the observed minus expected squared divided by expected, where the sum is over the k different categories. The p-value is the area to the right of chi-squared under the density curve of the chi-square distribution with k-1 degrees of freedom. So that is all the fixins. Right. Is there anything I can clarify before we move on to the questions that you will be trying to answer? So let's go to the first question. We're computing expected counts. We have our context here. Jenny made a 6-sided die in ceramics class and rolled it 60 times to test if each side was equally likely to show up on top. Assuming that her die is fair, calculate the expected counts for each possible outcome. Right, so we can have the number on top be 1, 2, 3, 4, 5, or 6. What is the expected count for each value? All right. So we've got a few people got it correct, a few people who seem to be still working on it. So I want to point out, in this context, we're not told exactly what the proportions are of each side, right? What our claim is or what the assumed proportions are, right? What do we have in the context that tells us what that is, though? In that first paragraph, what key piece of information can tell us how to calculate how many times each of those numbers should come up? So Alexis has here that the dice is 6-sided. That is true, right? So we know how many sides there are. We know something about the likelihood of each side happening, though. What does the paragraph say about the likelihood? It is rolled 60 times. We do need that for our calculation. How do we figure out how many times each number shows up? Out of those 60 rolls, how do we determine what the expected count is? What did you do to find it? Okay, so Jose, you've got 1/6 times 60. How did you know to use 1/6?
It's the probability of one side of getting one, or like 2 or 3 or 5 or 6.
Right, so it's the probability of each side showing up, right? We know that, though, the evidence, so to say, of that is that we're told if each side was equally likely, right? That's the part of this phrase that tells us 1/6 is what we can use. Each side has a 1 in 6 chance of showing up because it should be equally likely. That's what we're testing, right? The claim is that this is a fair dice, meaning that each side has the same probability of showing up. So we should be able to divide the 60 rolls by the 6 sides and get the expected count. Okay, if it's a fair die. If we were to roll the dice 60 times and our observed counts don't end up supporting that, we could have an unfair die. Right, so in this case, all of these are the same. They're all 10. Okay, each side should be equally likely, meaning we should get 10 of each side expected. All right. Is there anything I can clarify about this? Because there will be times where you're not told specifically what the thing is you need to multiply or divide by to get the expected count, but it will be implied in the context. So here's our next question. We're going to do expected counts again. However, this one is not an equally likely situation. Right, so we have a company that claims that each batch of its deluxe mixed nuts contain 52% cashews, 27% almonds, 13% macadamia nuts, and 8% Brazil nuts. To test this claim, a quality control inspector takes a random sample of 150 nuts from the latest batch. Calculate the expected counts for each type of nut. All right, let's talk about this one. So it looks like a lot of you are on the right track if you're working on it. Yeah, most of you have a lot of the right stuff going. One thing I do want to comment on is for expected counts, it's okay to have a decimal. We don't need all of them to be whole numbers. When we look at our observed numbers, those should probably be whole numbers because we're actually conducting the experiment. We can't end up with half a person or half of a number on a dice or something like that. But for expected, since we're doing averages and things like that, when we're doing expected counts, decimals are okay. So if you got a decimal and you didn't write it down because you weren't sure if you're supposed to use a decimal, decimals are okay. All right. So our expected counts here for cashews should be 78, I believe. It'll tell us it's correct. All right, and then we should have 40.5 almonds. All right, 19.5 macadamias, and 12 Brazil nuts, right? We got each of those numbers by multiplying the sample size by the probability of each of those nuts being in the distribution based on the claim, right, or null hypothesis, essentially. So we had 150 times 0.52 for 78, 150 times 0.27 for 40.5, 150 times 0.13, and 150 times 0.08 to get those different counts. Again, remember, the values we use for our chi-square test will be the count, not a percentage, not a proportion. Okay. Is there anything I can clarify on this one? Any questions? All right, move on to the next one. All right, so now we have to write our hypothesis for the same context. All right, we have that same company with their deluxe mixed nuts and their claim of what that distribution should be. We want to state appropriate hypotheses for performing a test of the company's claim. Now, remember, it's easier just to write these as statements. Right? Our null hypothesis is that essentially their claim is correct. The alternative is that their claim is not correct. You need to fill in the proper context to finish those out. Okay, so we'll give you a few minutes there to write those up, and then we will discuss. All right, so let's talk about this. So our null hypothesis should be basically that the company's claim is correct. I think one of the, I'd say the cleanest hypotheses that I saw basically use the strategy of, okay, well, their claim is that, is this part. So our null hypothesis is that the company's claim that each batch of its deluxe mixed nuts contain 52% cashews, 27% almonds, 13% macadamia, and 8% Brazil nuts is true. Right? All we basically do is take that whole sentence and then just say is true at the end. And we've gotten the null hypothesis. We take that same exact word for word thing and then just say is not correct for the alternative. Right? That's one of an actually very good strategy is if you have the context like that it's written out nicely for you, copy it for your hypothesis, and then just say their claim is correct or is not correct based on whether it's the null or alternative. Right? There's no reason to work extra hard to try to reword it. Right? It's already written nicely here. Okay. Is there anything I can clarify here? Right. So we now have hypotheses. Hooray. So now we will calculate a chi-square statistic for the same context that we've been using for previous couple questions. We're going to use the table below to calculate the chi-square statistic for the distribution. Please type the value of that test statistic in here. I don't need the equation. I don't need like all the numbers you added up, just the final answer for the chi-square statistic. Okay, you may want to look back to screen 3 because that has our formula on there if you need to use that. But you have the observed and expected counts to use to calculate your test statistic. I'll give you a few minutes here to calculate this and then we shall discuss. All right, so let's look at this real quick. So I'm going to quickly go back to that third screen. So here's our chi-square statistic formula. And we need to add up each of these 4 fractions here. Each fraction uses the observed and expected counts for one of our 4 categories of nut, right? Almonds, cashews, macadamia, and Brazil. All right. So we'll be adding up 4 fractions. based on their observed and expected counts. And let us see, where did I go? There it is. All right, so if we do this, we should get 6.59876, blah, 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 blah. Big old decimal, right? Let's see if I can get this. There we go. All right. In our calculator, we can type in our fractions like just the same way as we would write them, which can be very helpful. If you don't know how to do that, you go alpha, y equals, and hit enter. You get a little fraction doodad, which can be very helpful in making things calculate the way that you want them to. All right, so there is that. So this first one here, 83 minus 78 squared divided by 78, right? That's the observed minus expected divided by expected and all that stuff for our first category of nuts. Then the next one, and the next one, next one. We get a value for each of these, we add them all up, we get 6.5987, blah, 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 right? This is the best way to do this in your calculator to get the most accurate result. If you calculate each part individually and then add those up, you might end up with a rounding error depending on how you're rounding, which could make your result too different than what it should be. Right? The best way to do it is try to get your calculator to do it in one go, so you get one value and round that. For the rounding of this, where'd I go? There it is. Right? We never really keep more than about 3 decimal places. Most of our values on like our tables don't go past 3 decimal places. So we're going to round to 3 decimal places, right? So we get 6.599. If we wanted to round to 2, that would round the whole thing down to 6.6. If we want to round to 1 decimal, 6.6. Right? Using our just basic rounding rules, if the number to the right of the place that you're rounding to is greater than or equal to 5, then you round up. Less than 5, you round down. Okay. So we get 6.599 or 6.6, basically. If you were to round this to 6.5, that would be incorrect. You've rounded too much off. All right, so we get woohoo. I tried to build in self-checking things this time. All right, so we get 6.599 as our test statistic for our chi-square statistic. We'll need this for our next part. Are there any questions? Anything I can clarify? Good. Next, we're going to check large counts and find our degrees of freedom. Same exact context. We're going to confirm that the expected counts are large enough to use a chi-square distribution to calculate p-value. So is the large counts condition met? Yes or no? Remember, our large counts condition is that each of the expected counts is at least 5. Then, what degrees of freedom should you use? Based on the number of categories, what is the degree of freedom? So we'll answer these 2 questions here. The first submit button submits your yes or no answer. The second one submits the number. It should tell you if you're correct. All right. So we're a bit all over the board here. That's okay. We'll make sense of this. All right, so our large counts condition for our chi-square test for goodness of fit is that all of the expected counts for the categories in our categorical variable are at least 5. If we go to the previous screen, here's our expected counts. 78, 40.5, 19.5, and 12. Those are all greater than 5. Our large counts condition has been satisfied. So we'll say yes. Hooray. What are the degrees of freedom that we should use? Right? We have 4 categories. Right? Cashews, almonds, macadamia, and Brazil. Right? We have 4 categories. That means our degree of freedom will be 4 minus 1 or 3. Remember, in this case, when we're doing chi-square test for goodness of fit, the degree of freedom is not dependent on our sample size. The degree of freedom depends on the sample size when we're doing z-tests, right? We're doing 1 sample or 2 sample z-tests, or not z-tests, t-tests, sorry. Remember when we're doing means, all right? But in this case, it just matters about how many categories we have. We do 1 less. Is there anything I can clarify here? Any questions? So next, we're going to use table C to find the p-value and then write a conclusion. Same context. Right, now that conditions have been met, we have the value of the test statistic, that's 6.599, and you know the degrees of freedom, 3. We need to use table C to find the range of the p-value. Now we have the link here for our formulas and tables. You can click on that. It'll go right to the formulas and tables within Canvas. Right? And so just write in here what the range for the p-value is. Right? So after that, write a conclusion that you would draw about the company's claim distribution for its deluxe mixed nuts and justify your answer. Remember that since no significance value was stated, we should use alpha equals 0.05 as our default. Give you all some time here. If you have questions, let me know, and then we shall talk about it. All right, let's talk about this. So we need to use degrees of freedom 3, and the test statistic is 6.599 on table C. Right, so if we go to our tables, which I think I have somewhere, maybe I don't. There. All right, so we have table C here, and we're looking in this 3rd row for degrees of freedom 3, and we'll follow this up to here. 6.599 falls between 6.25 and 7.81. Right. We then go up to the top of the table where we have our tail probabilities, P, which is the p-value. And that means that our p-value must be between 0.05 and 0.1. Right. We will not get an exact value for P. We're not going to have p-value equals something when we use table C. If we want an exact value, we have to use our calculator. We haven't seen how to do that yet. Okay, so we get a range between 0.05 and 0.1, which means the p-value is greater than 0.05 but less than 0.1. So in our box here, we can type this out as 0.05 is less than our p-value, which is less than 0.1. And if we want to make it look nicer, we just highlight and hit that guy. All right, so that describes the p-value. It is greater than 0.05 but less than 0.1. Right, when it gets to the conclusion, we still fall back on the same basic rules about p-values and alpha. If the p-value is less than alpha, we reject the null hypothesis. If it's greater than alpha, we fail to reject the null hypothesis, right? Our p-value is greater than 0.05. It's right there in our interval. So since our p-value is greater than alpha, we fail to reject the null hypothesis. We do not have evidence that the distribution, we do not have evidence that the claim, right, the company's claim that their distribution of deluxe mixed nuts is different, essentially, right? So essentially, the evidence says that they are more or less correct about their claim. Now, we don't want to say that in stats. We don't say that something is correct or incorrect. We just say we have evidence for or against it. This evidence is for their claim. What questions do you have? What can I clarify? All right. So last thing we're going to talk about is our follow-up analysis, which was briefly talked about yesterday in the lesson that it actually didn't talk about. And so we'll do a quick little blurb on that. All right, when a sample data lead to a statistically significant result, we can conclude that our variable has a distribution different from the one stated, right? Which we did not have in our example. When this happens, start by examining which categories of the variable show large deviations between the observed and expected counts. Then look at the individual terms, observed minus expected squared divided by expected, that are added together to produce the test statistic chi-squared. These components show which term or terms contribute most to the chi-square statistic. Determining which component contributed the most to the chi-square statistic will allow us to get an idea of which categories have incorrect hypothesized values. All right. So to put this into an example here, we saw this example yesterday in the lesson with the hockey players, and there was a claim that hockey players born earlier in the year have an advantage, right? They'll be more successful just because they get more coaching, they're a little more mature than the people they play against, they get more playing time, all that stuff, right? And if we look at the components here, the 4 categories and their component, right, what they've contributed to the chi-square statistic, our largest component is the 7.2 with the January through March quarter. Right? It contributed the most to our chi-square statistic, right? Which is basically it's the most convincing evidence that the original claim, right, or our null hypothesis is not correct. Right? It also provides evidence towards what the author of this study said, and that's people who are born earlier in the year have an advantage. Right? So we can use this idea of like that follow-up analysis to look back at the data and say, okay, well, what things contributed to this result the most? And based on what those things are, what can we say about, what else can we say about our results? Right. I don't need you to answer the question that's attached to this, so we just talked about it, so that's it. Is there anything I can clarify about this follow-up analysis, as they call it? We'll stop sharing my screen. There we go. All right, so that's the practice for today. That's your participation and such. I hopefully will have the practice problems, maybe not their solutions, but at least the problem set for section 11.1 ready today or tomorrow. but I should have like the rest of my materials for chapter 11 done by the end of the week. So look forward for those. If you need more practice with this, definitely I suggest doing those practice problems when they're available. If you have any other questions, comments, or concerns, please make sure to let me know. You can stick around after this call and talk to me, or send me an email, send me a message, something like that. But besides that, I hope you guys have a great rest of your day, and we will see you next week. Have a great weekend.